Okay, in today's demonstration I have an electrical circuit and we have a step response of this electrical circuit. Now the amazing thing about this step response is the oscillations coming over here. Now the question is that why we are having these oscillations in this step response. So first of all, we would just like to understand why these oscillations are created in any physical system. For this actually we have a demonstration over here. You can see this is a pendulum system. In any system, oscillations are created whenever the energy is converted from one form to another form and then back to the original form. For example, in this system, if I take this mass to a height, for example h, now I have actually stored potential energy, or I have given potential energy to this mass. If I release it, this potential energy is converted into kinetic energy and then back to the potential energy and then to the kinetic energy. So this conversion of energy from potential energy to kinetic energy and then back to potential energy and then to kinetic energy causes the oscillations. So this is the cause of oscillations in any physical system. Now in electrical systems, for example, let us consider this RLC series circuit. So in this RLC series circuit we have an inductor and a capacitor over here. Now the capacitor stores the energy in the form of electric fields across its plates, while the inductor stores energy in the form of magnetic field because of the current flowing through it. So oscillations are generated when the energy flows from the capacitor to the inductor and from the inductor to the capacitor, and this back and forth flow of energy causes the oscillations. Now what is this resistor doing over here? What is the purpose of this resistor? This resistor is actually an element that can actually dissipate the electrical energy to the surrounding system in the form of heat. So if I choose a specific value of this resistor such that all of the energy that is stored in the inductor and the capacitor is dissipated equally by using this resistor, then actually I can create a critically damped system. Okay, let us have a look at this demonstration. For example, now what I am going to do is that I have just changed the time scale. Now I am just going to introduce a resistor into this system, and as I introduce a resistor into this system, you see that the oscillations have been removed. So by applying this resistor over here, you see that we got a very critically damped response. Now the question is that did I just place some random resistor into this circuit, or was there some calculation behind this all the application? Actually what we did was that we just applied Kirchhoff's voltage law across this circuit, and then we got the differential equations of this system. Now from the differential equations of this system, we just applied the Laplace transform to the both sides and calculated the transfer function, and the transfer function is basically a second order transfer function, and we can just compare it with the standard equation of a second order system, from where we can actually calculate the value of zeta, which comes out to be this one. Now what we did was that we just calculated the value of R for zeta is equal to 1. So the value comes out to be 22.8 kilo ohms resistor. So the response that you looked over here on the oscilloscope when I connected the resistors with it was actually critically damped because I added a resistance of 22.8 kilo ohms in series with the RLC circuit. Now for this demonstration I have used L is equal to 13 Henry, which is basically the primary coil of this transformer, and I have used the capacitor of 0.1 microfarad, non-polar capacitor of 0.1 microfarad, and this transformer has an internal resistance, the winding of the coil has an internal resistance of 1.8 kilo ohms. So, this was about this demonstration. Thank you.